Hello. Now let us discuss another method to solve partial differential equation of the form, particularly for the form of Lagrange linear equation. Okay, so this is a particular kind of partial differential equation, which is a linear partial differential equation of the form P plus QQ equal to R. We'll learn how to solve this kind of differential equation by using Lagrange multiplier and grouping method. Okay, a linear partial differential equation of first order is particularly known as Lagrange linear equation if that linear equation is of the form P plus QQ equal to R, where capital P, capital Q and capital R functions of x, y, z, and we know P and Q, small p and small q, right? So as we discussed in the earlier class, small p is nothing but dou z by dou x and small q is dou z by dou y. Okay, so if we have an equation like P plus QQ equal to R, form of P plus QQ equal to R, we call this equation as Lagrange linear equation, and actually which is obtained by eliminating arbitrary function phi from the particular equation, phi of u equal to 0. In other words, if you solve this kind of partial differential equation, we intend to get a solution like this. So this is a two-way process. One is to get a partial differential equation by eliminating arbitrary function. Okay, by eliminating arbitrary function, or in the other way, we can form or we can solve this partial differential equation and form its solution. Okay, so here we will solve the partial differential equation of the form P plus QQ equal to R and try to get a solution of this partial differential equation, which is obviously of the form Q of uv equal to 0, where u and v are some functions of x, y and z. Now let us see how to solve Lagrange linear equations and find its solution. Okay, so partial differential equation of the form P plus QQ equal to R. So first of all, whenever you get a questions like this, you have to identify first of all capital P, capital Q, capital R. Actually, capital P is nothing but coefficient of small p. We know what is small p, dou z by dou x. Whenever you see small p, you have to think about dou z by dou x, and small q is dou z by dou y. So whatever is the coefficient of or thing other than small p, you can put as capital P. Okay, whatever in the term whatever is other than small q, you can put as capital Q, and other variables which does not contain small p and small q can put as capital R. Like this way, you have to identify capital P, capital Q and capital R. Then you form subsidiary equation like dx by capital P equal to dy by capital Q is equal to dz by capital R. Now you can solve the partial differential equation by grouping. That means if you take any of these two, either these two or these two or these two, any of these two equation, and then you equate that, sometimes you will be getting an equation with the separated variables. That means only x with the dx and y with the dy or z with the dz. Okay, so you can separate these variables and you can directly integrate to get the answer. Sometimes that is not possible. Okay, you cannot separate assets. In that case, you can use method of multipliers. We'll say understand, or we'll discuss method of multipliers in detail. And also you can use any combination of these two. Okay. Finally, you have to write the solution as u equal to a and b equal to b. Okay. And the complete solution is given by or written by phi of u equal to 0 or u equal to f of v. So we write a solution in this form whenever you get solutions like u equal to a and v equal to b. So you have to write solutions as function of u equal to 0 or this form, or form of u equal to f of v. Okay. Now let us see one question to solve linear equation or linear partial differential equation and find the solution. Okay, so the question asks y square is at divided by xp plus x is at q is equal to y square. Okay, so this was the question. Okay, so by mere examination we can rewrite this question a little bit, or you can multiply all term with x so that you will get some more neat differential equation like this. So y square into 2p plus x square into zq equal to y square z. So this is actually z, not 2. Okay, this is okay. So this we get subsidiary equations as, so we put whatever you have other than p, you put this as capital P and you put this as capital Q, and this we can take this as capital R. So this is R, this is Q, and this is P. So you can write dx by capital P, so dx by this, dy by capital Q, so dy by this, and dz by capital R. Okay, so these are the subsidiary equation. Now you can compare or group first two factors, that is dx by y square z equal to dy by x square z. So in this we can cancel z, so what remains is dx by y square equal to dy by x square. So cross multiplying which will give you x square dx is equal to y square dy. Okay, so you can integrate this, so you get what you get is x cube by 3 is equal to y cube by 3 plus a constant c. Or you can multiply all this with 3, you get x cube equal to y cube plus 3c. Okay, you can put again, you can put some constant as a. Okay, 3c equal to a, you can put 3c equal to a. Okay, so x cube minus y cube equal to a. Fine. Now after this you can compare other two. Okay, first and third, you can compare first and third. So dx by y square z equal to dz by y square x. In this you can cancel y square. Okay, so what remains is dz by dx by z is equal to dz by x. On cross multiplying you can separate these variables, so what you get is x dx equal to z dz. So we can clearly see that you have separated these variables, so we can directly integrate now. So what you get is x square by 2 is equal to z square by 2 plus a constant c. So you can write as x square equal to z square plus 2c. You can put 2c as b, say another constant b, or x square minus z square equal to some constant b. Okay, so you get two solutions. One is this, okay, one is this, and other is we have already found second one. Second one is this. Okay, so you can write first solution and second solution either in the form of some function of or phi of or f of x cube minus y cube, okay, comma x square minus z square equal to 0. That is f of uv equal to 0 on the form of f of uv equal to 0. Or you can write the same solution in the form of x cube minus y cube equal to some function of x square minus z square, that is u equal to some function of v. So these are two typical way to represent the solution. One is this f of uv equal to 0, or other is u equal to f of v. So you can write any of this form. So the general solution is like this representation or like this representation. This is how you solve a particular Lagrange linear equation by using subsidiary equation and grouping. Okay. Now let us do another problem. So solve a linear partial differential equation of the form pp plus qq equal to r. So clearly you can see that this particular differential equation is the form pp plus qq equal to r, where is dou. So this is p, small p, and this is small q, where you can also identify this is capital P and this is capital Q and this is capital R. So now you can form subsidiary equation as dx by capital P is equal to dy by capital Q is equal to dz by capital R. Okay, first of all you have to look at this subsidiary equation. If you can group and eliminate or collect variables together, that is fine, but here it is a bit difficult to collect the variables and do the direct integration. So you need to use method of multipliers. You can use multipliers x, y, and z. The choice of multipliers is based on your experience, or you just need to find whether you can get some denominator as 0. Okay, so that is what we are intended to do. Okay, so I'll explain how to choose this denominator after one problem. Okay, so first of all you need to use multipliers x, y, and z. That means you multiply the first relation or ratio with x. Okay, numerator and denominator with the x. So x dx divided by x into m z minus ny. Okay, so second ratio was y dy. So we are multiplying numerator and denominator with the y into nx minus lz. Third was z into dz divided by z into ly minus mx. Okay, ly minus mx. So then you add this all. Okay, so since all the ratios are same, we can say that we can directly add this together because the ratios are same. So no need to find common factor, etc. Okay, so finally what you get is x dx plus y dy plus z dz divided by x mz minus x ny plus y nx minus y lz plus z ly minus z mx. You can see that x mz and z mx you can cancel, l y z and z ly you can cancel, y nx and x ny you can cancel. So finally what you get is x dx plus y dy plus z dz divided by 0. Okay, but you have to keep one thing in mind. Since all these ratios are equal, we can also say that this is equal to the ratio we have identified by using multipliers. So x dx plus y dy plus z dz divided by all these three are equal, so the fourth one is also equal, this is also equal. So say we can put as this lambda. Okay, so finally what you get also will be equal to lambda. That means x dx plus, that means x dx plus y dy plus z dz equal to 0. Okay, so see here you can directly get the variable separated form. So now you can integrate. So what you get is x square by 2 plus y square by 2 plus z square by 2 equal to c, or you can say x square plus y square plus z square equal to 2c. You can put 2c as small as, since all are constant, you can put 2c, you can name 2c as a. So now you got one step. You can now go to next step to find the solution. Again you look on the auxiliary equation. Okay, on the auxiliary equation. So this was the auxiliary equation you have to focus on. Now you choose multipliers as L, M and N. Okay, you can choose multipliers as L, M and N. So L dx divided by L into M z minus Ny. Then next ratio is M dy divided by M into Nx minus Ly, Lz, and third was N. Okay, third was N. So N dz divided by N into Ly minus Mx. Okay, so since these three are equal, you can just add this. So finally what we get is L dx plus M dy plus N dz divided by L mz minus L ny plus M nx minus M lz plus N ly minus N mx. So this you can cancel, M lz can cancel, L ny and N ly you can cancel. So what remains is L dx plus m dy plus n dz divided by 0. Since we have all these three ratio are equal, so we can also say that this is equal to this thing. Okay, so let us put this is lambda again. So all these three ratios are equal to lambda, and the ratio we made also equal to lambda, because all these are equal to lambda equal. Okay, so this thing is equal to lambda, so that means L dx plus m dy plus n dz equal to 0. So now you can integrate with respect to each and every component. Okay, so integral L dx plus integral m dy plus integral n dz equal to 0. That means Lx plus my plus nz equal to any constant b. So now we receive two particular relations. One is x square plus y square plus z square equal to x square plus y square plus z square equal to a, and Lx plus my plus nz equal to b. Now you can write solution as phi of x square plus y square plus z square comma Lx plus my plus nz equal to 0. This is of the form phi of u equal to 0, or you can even represent like this way, but we have written here x square plus y square plus z square equal to some function of this is u equal to f of v form. So this is how we solve equation by using multipliers method. Now let us see another example. We have to solve this partial differential equation x square minus y square minus z square p plus 2xyq is equal to 2xz. So first of all, you need to identify capital P, capital Q, capital R, and form subsidiary equation dx by capital P is equal to dy by capital Q is equal to dz by capital R. So finally we can write subsidiary equation or subsidiary equations as this. Okay, now you can see these two things. Okay, these two things, because clearly you can say that by equating this you can separate variables. Okay, by equating these two we can cancel 2x from both this equation. So finally what we get is dy by y equal to dz by z, or dy by y minus dz by z equal to 0, or you can write this is equal to log integrating. You can directly integrate this. Okay, so log y equal to log z plus log a. I deliberately put constant as log a because when you rearrange and find anti-log or the reverse form, you can write it as a. Okay, that means log y minus log z equal to log a. That means log y by z is equal to log a. That means y by z equal to a. So we got one solution. Now you check for some other solution. Now again we have our auxiliary equations. The equation, subsidiary equation as this. Okay. Now we use multipliers x, y, and z respectively. Okay. Since these are the subsidiary equation, we can take this. Okay. So you can multiply x, y, and z in numerator and denominator, x, y, and z. Now you add this x dx plus y dy plus z dz divided by x into x square minus y square minus z square plus 2x square y, sorry, 2xy square, 2xy square plus 2xz square. So finally what you get is, you can say that this is equal to x dx plus y dy plus z dz divided by x into y square plus z square. Okay, you can see here. So now you compare, see here, as you see this auxiliary equation, these three components are equal, and what we develop is developed is also again equal to these three. Okay, so you can compare any three of this equation, and likewise we can compare the equation that you formed with any of these three equations. Okay, you can compare equation that we formed with any of the three equations in the subsidiary equation. Okay, so we compare this with the third unit of the subsidiary equation, third unit of the subsidiary equation. So see here. Okay, so clearly you can cancel x, and what you get is this thing, 2x dx plus 2y dy plus 2z dz divided by x square plus y square plus z square equal to dz by z. So this in turn gives log x square plus y square plus z square equal to log z plus, say, some constant log b. So you're taking log z into left hand side, you can say, and taking anti-log. So you can say that x square plus y square plus z square divided by z is equal to b. So we get two things. So we can write the solution as x square plus z square plus y square, x square plus y square plus z square divided by z is equal to f of y by z, or you can multiply with z and form x square plus y square plus z square is equal to x square plus y square plus z square is equal to z into f of y by z. Now let us go to discuss another problem. X square into y minus zp equal to y square into z minus xq is equal to z square into x minus y. So first of all you need to form the subsidiary equations, then you think of multipliers. Okay, here suitable multipliers is 1 by x, 1 by y, 1 by z. So multiplying, we get 1 by x dx plus 1 by y dy plus 1 by z dz divided by, so what you get is 1 by x dx plus 1 by y dy plus 1 by z dz divided by x into y minus z plus y into z minus x plus z into x minus y. So this thing in the denominator becomes 0. Since each of the fraction is equal, this is equal to this. Say it is equal to lambda. Say this is equal to lambda. That means 1 by x dx plus 1 by y dy plus 1 by z dz divided by 0 equal to lambda. That means 1 by x dx plus 1 by y dy plus 1 by z dz equal to 0. That means on integrity you get log x plus log y plus log z equal to log a. So taking antilog we get x y z is equal to a. Now you look for another multiplier. You think about another multiplier. Clear it is x square, y square and z square. So multiply each points in the auxiliary equation with the x square, y square and z square. Then what you get is x square dx plus y square dy plus z square dz divided by component wise multiplication. Okay. So here also denominator will become 0. That means each and every component or each and every ratio in the subsidiary equations are equal, and here what we formed is also equal. So let us that equal to lambda. That means 1 by x square dx plus 1 by y square dy plus 1 by z square dz equal to 0. So on integrating what we get is 1 by x dx, 1 by x plus 1 by y plus 1 by z is equal to a. So now you can write in some form for the general equation. So 1 by f of 1 by x plus 1 by y plus 1 by z is equal to x by z, or f of 1 by x plus 1 by y plus 1 by z comma x by z equal to 0.